Hi, everyone. Welcome to APCTP String Seminar. It's a great pleasure to introduce today's speaker, Noah Miller. He is a PhD student in Harvard University, and he recently worked on the very interesting topic on this matrix model with Andy Strominger. Today, he will tell us about this work called this soft Graviton Theorem in BFSS matrix model. Please join me in welcoming our speaker, Noah.
Oh, thank you. Yeah, so this is a joint work from me, Tianli Wang, Adam Chopper, and Andrew Strominger. Okay, so what's important about the BFSS matrix model for, I guess, Andy's group and considerations of asymptotic symmetries is that it's an explicit example of a flat space holographic duality. So just really basically what the topic of the paper is, we're trying to fill out this duality dictionary. So I'll explain this a little bit more in a minute, but M theory in 11-dimensional flat space is dual to a very special matrix quantum mechanics, just 0+1 dimensional quantum mechanics describing D0 branes in 10-dimensional space, okay? But in 11-dimensional flat space, we have soft gravitons and we have asymptotic symmetries, namely supertranslations. So what are the dual concepts of these two things in the matrix model? And that's sort of the question which this paper answers. So in order to understand what I just said, I'm going to first give an introduction to BFSS. Whoops. Sorry. Yeah. I'm going to give an introduction to BFSS and also an introduction to asymptotic symmetries. And then we'll talk about soft gravitons in BFSS. So, sorry. So first, sorry, wait a second. This isn't the right, oh, shoot. Oh, darn. Sorry, this is actually not the, I thought something was wrong. This is the wrong PDF. Okay. Okay, sorry about that. So we're going to present first what are asymptotic symmetries, then we're going to talk about what BFSS is, and then we'll combine the two. Okay, so first, what are asymptotic symmetries? Well, there's this motto that the asymptotic symmetry group, which I've labeled with mathcal G here, are the set of gauge transformations that preserve a certain set of fall-offs modded out by small gauge transformations. So let's give a very specific example of just U1 Maxwell theory in 4-dimensional spacetime. So if we define the retarded time U as just T minus R, where R is the radial coordinate, and that gives a very specific form to the metric, where here just gamma AB is the sphere metric, and A labels the two sphere coordinates. Then if you study solutions, radiative solutions to Maxwell's equations, you'll find that AU, AR, and A sub A, the sphere coordinates, have certain fall-offs for radiative solutions, just from point charges, wiggling around and stuff like that. And the AU component goes off as 1 over R, the A sub R component goes off as 1 over R, and the A sub A component will actually be some O of 1 constant at large R. We're studying null infinity here. So these are the fall-offs for Maxwell theory. And of course, you have these gauge transformations. So we vary A sub U as the U derivative of some function theta. We vary A sub R as the R derivative of some function theta, and A sub A is the A derivative of some function theta. And what fall-offs must theta have in order to preserve the fall-offs on A, right? So once you have these boundary conditions for the gauge field, We only want certain gauge parameters theta that satisfy these fall-offs. And we can see that this first one is the most important, that a sub u goes as 1 over r. To leading order in r, the limit as r goes to infinity, the u derivative of theta must be equal to 0 in order for a sub u to still fall off as 1 over r. All right, now you could say that maybe I should have written partial u of theta is like O of 1 over r, but I'm really just sort of interested in this leading part of theta for my own purpose. Just maybe it's a little clearer to write that way. Maybe I should have written O of 1 over r. But the point is that, the leading order theta must be constant in retarded time u on null infinity in order to be part of the asymptotic symmetry group. So that means that there's a whole sphere function, function on S2, the sphere, worth of one function on the sphere worth of an asymptotic symmetry group, right? So the asymptotic symmetry group is parameterized by one function on the sphere because theta has to be constant in u. So from a gauge symmetry, right? This is a totally general gauge symmetry. This will be a symmetry of the action for U1 Maxwell theory. And we know from Noether's theorem that from any symmetry, we can compute a Noether current. So this is actually something which is, there's some incorrect stuff in literature about this. Like especially if you look at old sources, people will say that, Noether currents from gauge symmetries are like 0 or they don't mean anything and they're trivial. That's totally not true. Okay, this is a symmetry and you can compute a non-vanishing, gauge invariant Noether current from this gauge symmetry, and that has a meaning. If you integrate that Noether current, you get something called the soft charge. And well, we'll talk about this right now. So so if you just use textbook Noether's theorem, this is what you get for the Noether current here. It only involves F mu nu and not A mu. So it is a gauge invariant current. It depends on this parameter theta, but that's not, theta is sort of an external parameter, right? Like theta gives a one parameter family of gauge transformations, but this current is, gauge invariant. That's a little bit of a subtlety. You can see it's a generalization of electric current, charge current, because if theta is equal to 1, then this part is 0, and then this is just the charge current.
So is it because you have the asymptotic infinity? Like for example, if you consider some Maxwell theory on the compact space, do you still have this kind of current, or this current is only?
This current can be derived totally independent of any considerations about the topology of spacetime. But I think I'll address. Yeah, I think I can address that. I think I know what you're thinking, and the thing is that on a compact space, there won't be a notion of a charge. The charges will be trivial for the following reason. So if you use the equation of motion, you can rewrite this current as a total derivative of a 2 form. And thus, if you were to integrate this over a surface without boundary, right, then this would be 0. So in a non-compact space, like, the world we live in, and you have a very large Cauchy surface, which has a boundary at infinity, this won't be 0. So yeah, so it's actually a boundary. So the charge will actually be a boundary charge whose values only depend on the boundary, but it's still non-trivial nonetheless. So this is a feature, by the way. Any sort of Noether current, just from Noether's first theorem derived from a gauge symmetry, can always be written as the total derivative of some 2 form. This is a fact which is very kind of well known and used, but I think most people are not aware of a general proof, though there is actually a general proof of this fact. It's sort of a good way to understand what's sort of strange about Noether currents from gauge symmetries, that they always end up being local divergences of two forms. But it doesn't make them trivial, it just makes them actually more interesting. So if you take future null infinity as a Cauchy surface, your final Cauchy surface, and you take past null infinity as some initial Cauchy surface, and you compute and you just integrate the current over these two Cauchy surfaces, then you'll get a charge from these. You'll get a charge QF and QI. And because it's a conserved current, QF equals QI. And if you explicitly write out this equation, you go through all the steps, you write it out in great detail, you'll find that this conservation equation is actually the soft photon theorem. And so if you have, say, two charged particles like electrons, doing something and scattering in the space-time, something in particular, and they'll have all this electromagnetic radiation, you can see that the charged particles, like the electrons, those have this J mu here, while the photons will have this F mu nu here. And so there's some interplay between what's going on with the photons and what's going on with the charged particles. And it ends up amounting to the soft photon theorem in the context of quantum field theory. It also is I will now just briefly plug a review paper I wrote, which I wrote sort of at the level of maybe a beginning grad student or an advanced undergrad who only knows Maxwell theory, just going classically through all this Noether theorem stuff and showing, for instance, how you get the soft photon theorem and what the physics is of this. It's almost all classical physics. So I'll just briefly plug that. Okay. Now, if you do a partial gauge fixing, like Lorentz gauge, which is just partial mu a mu equals 0, then there'll be some residual gauge transformations which also satisfy Lorentz gauge, namely thetas which solve the wave equation, partial squared equals 0. If you do a gauge transformation by such a theta, A will still satisfy Lorentz gauge. Now you might be saying wait a second, Noah, what do you mean a partial gauge fixing? I thought, you were thinking about all these gauge transformations and asymptotic symmetry groups. Why are you talking about partial gauge fixing? Well, let me explain. So let's say we have what I said in the beginning, we have some asymptotic symmetry group, which is allowed gauge transformations divided by trivial gauge transformations. If you choose very carefully choose partial gauge fixings, a very good partial gauge fixing can get rid of all the trivial gauge transformations. And by trivial, I just mean, say, a theta with compact support in the bulk that goes to 0 on the boundary. That's what I mean by trivial, like a small gauge transformation, not a large one. And then you now get rid of some of your allowed gauge transformations, but there'll be still some residual ones. Then if you choose a really good partial gauge fixing, you'll actually still get the same group in the end. And the Lorentz gauge is actually such a good partial gauge fixing. So if you have a theta, right, a gauge transformation, a gauge parameter that satisfies the wave equation, then you can't have a little bump in the middle of the space-time because it will want to propagate out to null infinity. So you can't just have a little bump in the space-time because it's going to propagate out. So Lorentz gauge gets rid of these trivial gauge transformations. And then there'll be certain allowed ones that are U independent at null infinity, and these are the ones you want to study, and so forth. And the sort of very prototypical example of one of these allowed gauge transformations is what I've written as follows. Now, the form of this isn't too important, but just notice that here, okay, Q is a 4 vector. So X is a 4-dimensional space-time coordinate, and Q is a null vector that satisfies Q squared equals 0. And notice that this function has a scaling symmetry. If you multiply X by some scalar S, then it doesn't change the function. So in fact, theta only actually depends on the ratio of the space vector X divided by T at infinity, right? Because you can choose this, for instance, S equals 1 over T. And so the value of theta will actually become well-defined on rays, on like lines going out to, going out to asymptotic infinity. So this is a very interesting feature of such functions. Okay, so that was U1 gauge theory, which I think is sort of illustrative, and it's good to start with that. Now, if we go to gravity, just Einstein gravity in 4 dimensions still, there are a very special set of fall-offs in gravity. I just wrote this just to, you don't have to really digest this, but this is the Bondi metric. So radiative solutions in 4-dimensional gravity will have certain fall-offs with certain degrees of freedom. You have MB, UA, CAB, and they have relationships between each other, and they're functions that live on null infinity. And metrics of this form will have radiative fall-offs. And if you study which gauge transformations, in this case diffeomorphisms, preserve the fall-offs of this metric, you'll find that there's an infinite dimensional group of them called supertranslations. So for the purpose of this talk, so here Xi is a vector field, a supertranslation, and then the leading term is some function f on the 2-sphere times partial u, and then some other terms, which are also important, but just for the sake of simplicity, I'm not writing them. Just so this is the most important part. So here f is just any function on the 2-sphere. And that parameterizes these supertranslations. So it's actually, yeah, so it's sort of similar actually to the U1 case where it's parameterized by a single function on the 2-sphere. And the corresponding conservation law from this symmetry is the soft graviton theorem instead of the soft photon theorem. So here's how to picture a supertranslation. So here we have null infinity, and here we have the 2-sphere, although it's actually just a circle because we're reducing by a dimension. So here, these red lines are the vector fields of the supertranslation. And notice that they translate in U, they translate along U, but they change from point to point in the 2-sphere, right? So they stay the same along U, right? But on the 2-sphere, they take different values. So time translations, for instance, like just translating a time coordinate, that's an example of a supertranslation where f equals 1. If f equals the 3 different spherical harmonics, then you get the 3 space translations in x, y, and z. But then you also have an infinite number of new symmetries. Okay, good. So that's my spiel about asymptotic symmetries. Does anyone have any questions about this before I go into BFSS?
I have some one simple technical question. You divide by this trivial gauge symmetry when you talk the previous slide. Yes. So here you distinguish this allowed gauge transformation and the trivial gauge transformation. How can I distinguish them?
Okay. Yeah. So actually, yeah, I talk about that in that note. So the real way you tell is by closely studying the symplectic form of your field theory. And whether or not the vector field on your phase space is degenerate it corresponds if it's trivial or not. So for a gauge transformation, the vector field in phase space basically just amounts to a boundary term for a gauge transformation. And if your gauge parameter goes to 0 on the boundary, then the vector will also be degenerate. And if it goes to some non-zero thing, then it's not degenerate. That's like the mathematical way to tell the difference. You have a symplectic form. Is it a degenerate transformation or not? So you sort of like, you're not really, right. So you're sort of mathematically forced to conclude that large gauge transformations are physical.
So here, when you say the symplectic form is on the asymptotic infinity, or you just
it's in the configuration space of fields. It's not in space-time, it's in phase space. Symplectic form on phase space, yeah. Using the covariant, you could use, for instance, you don't have to, but it's usually most convenient to think about each solution to the equation of motion being one point in the phase space.
Okay.
And then you can compute the symplectic form of that.
Mhm.
Very good. Is there any of your questions? Or?
Can I ask you a question?
Yeah.
So you said that the gauge symmetry has a non-trivial, net charge.
Yes.
So are you going to give some specific example?
Not in this talk. This is just sort of setting up why we're interested in the paper. But I mean, there are lots. I mean, in lots of papers, these charges are written down. Although, I mean, it's just, yeah. I mean, I wrote the current. In the case of U1, I wrote the current here, and just integrating that.
Yeah, right. So what do you think about the statement that gauge symmetry is another symmetry, but
Oh,
redundant?
So small gauge transformations are redundancies. Large ones are not. Now.
Yeah, right. So then the question is whether the large gauge transformation is really anything that can be studied in local way.
In a local way.
Or is this symmetry?
Yeah,
Large
so
gauge.
certainly local, maybe. I mean, they do, if you write out the conservation laws coming from large gauge symmetries, they correspond to soft theorems, and they also correspond to something called memory effects. So for instance, the gravitational, if you just take the conservation equation coming from these conservation laws and you kind of manipulate them slightly, you can rewrite them as like, say, the gravitational memory effect or the electromagnetic memory. So they're actually new memory effects that people discovered by, I mean, doing this.
By large gauge transformation, what
Yeah.
you really means is that something which has a non-trivial winding numbers and
No,
so
it's
on?
nothing to do with that. That's a totally, yeah. That's another example. That's
So
sorry.
what is a large gauge transformation?
It's just a gauge transformation that doesn't go to zero at infinity. So in particular, you wanted to find some fall-offs for your theory, and they are ones that change the data at null infinity or even time-like infinity. But okay, let's just say null infinity. But don't, yeah, they change the data. Yeah, just a gauge transformation that changes the data at null infinity. Yeah, that's
I think that if you change the boundary condition, that means you are changing the gauge. So those are by definition the something which changes the boundary condition, right?
no, it keeps the boundary conditions. So the boundary conditions will, for instance, be certain fall-offs. Like AU. So in this example, we had AU goes as 1 over R, AR goes as 1 over R, A sub A will be like a finite number. And then the gauge transformations that preserve these fall-offs in R from radiative boundary conditions, that will have to have that the U derivative is 0 at the finite order. And so you still have a function on S2 worth of gauge symmetry that preserves the boundary conditions. Yeah, so for instance, here's another example though. So if you think about diffeomorphisms, right? I think most physicists would be comfortable with the idea that translations that like in space that give total momenta being conserved are physical transformations. You take the universe, you shift it over 10 feet to the left. That gives you, from Noether's theorem, conservation of momentum, and that has like so many physical consequences in colliders. Stuff collides, it's a physical symmetry. And how do you know that that's a physical symmetry, right? Because a philosopher might say, okay, if you shift everything over to the left, you haven't really changed anything. Like nobody in the universe could tell if everything was shifted over to the left. But the idea is that if you look at, for instance, the symplectic form, the transformation that shifts everything over to the left is non-degenerate. And so it gives you a non-trivial conservation law. So that's the sort of mathematically rigorous and philosophically agnostic way of determining if something's physical. and large gauge transformations are exactly the same as that. That's what I would say.
Yeah, but I wonder that if that is in order to keep the boundary condition, the gauge transformation should fall off much faster than those I mean the boundary
But that's
condition. And whether you can change, okay, whether there is any effect, I mean that gauge transformation at the boundary.
But that's the interesting part. That's what's so surprising, and why only until relatively recently has this field sort of really come into its own. Because you would think that, but if you actually look at the boundary conditions, it's not the case. And I mean, actually, I mean, that was even Bondi, Metzner, and Sachs basically sort of realized this in gravity with supertranslations, although maybe they didn't realize like the full physical implications of this. But they actually expected exactly what you said. They thought that if you were to study the radiative fall offs from gravity, then there should only be Poincare transformations. That's what they expected to get. And they were very surprised to find that there were supertranslations. That was actually very surprising to them. So it's a surprising fact of it's a non-trivial symmetry.
All right, thank you.
Oh, you're welcome. Cool. Okay, so now we introduce the BFSS matrix model, which is which there was a lot of activity on in, say, like 1998 or so, but not as much, but it's not as commonly known a topic now. So let me briefly introduce this. So we're switching gears completely for a minute. So think about just Kaluza-Klein theory in 5 dimensions as it was originally understood, by Kaluza and Klein. So if you have a graviton, just pure Einstein gravity in 5 dimensions, and then you compactify your space-time in a small spatial circle, this will decompose into a graviton, a photon, and a dilaton in 4-dimensional gravity. So now that's just if the graviton has no momentum along the circle direction, right? In 5 dimensions, if this graviton has no momentum in that circle direction, okay? But if it has n units of momentum, right, along the compact direction, then the 4D particle it corresponds to will have a mass, which will be proportional to its electric charge, which will be proportional to n, the momentum around the circle. So 11-dimensional supergravity has 3 massless fields, a graviton, a gravitino, and a 3-form field. And when 11-dimensional supergravity is compactified in a spatial circle, then one gets all of the massless fields of type 2A superstring theory. So M theory, we'll just say, is defined to be the theory which is type 2A string theory when one of the 11 spatial dimensions is compactified in a circle. So low energy, and the low energy theory of M theory is supergravity in 11 dimensions, and that includes gravitons. So there are gravitons in M theory. So the field in type 2A string theory, which corresponds to the photon or the 1-form field, will denote C sub mu, and that's the RR 1-form field, which I'll sometimes call the photon. And so one can ask, like, okay, so if you say that type 2A string theory is the Kaluza-Klein compactification of this M theory thing, then what are the Kaluza-Klein states that are charged under this 1-form field? And the only possibility you could ever think up are D0 branes. D0 branes are charged under the 1-form field, and therefore you would conclude, okay, 11-dimensional gravitons in M theory with a momentum around the compact dimension, those are bound state clumps of D0 branes in 10 dimensions, where the number of D0 branes, n, is the momentum of the corresponding graviton in 11 dimensions. So that's a bit of background. But here's how we transition to the actual BFSS matrix model. Okay. So if we think about compactifying the 10th dimension, right, here we have 11-dimensional space, and we make the 10th dimension, we identify it in a circle with this radius RC, R compact. And then we do a large boost in the 10th direction, right? Then this space-like circle if we do a very large boost, will become a nearly light-like circle. And the bigger the boost, the bigger this distance here becomes. So here we'll have x, is it x minus or x plus? X minus, okay. So here we're having x minus compactified with a radius of r. And the bigger the boost is, the bigger r gets. So what's very interesting is that if you make a very big boost, then this distance r becomes infinity and you recover the whole space-time. So here we have something very special. We have a small compactification radius here, but then we do a big boost and we get back all the lemma-dimensional space. So the BFSS conjecture from 1996 says that the light cone quantization of M theory, which is just M theory in 11 dimensions if you compactify a null slices, will be equivalent to a certain 0 + 1 dimensional quantum mechanical theory of n by n matrices, with n going to infinity, describing D0 branes moving in 9 + 1 dimensional type 2A string theory. So I'll elaborate a bit on that in a bit, but the idea of the original BFSS conjecture is that if you take clumps of D0 branes and you scatter them in BFSS, you will recover the same scattering amplitudes as if you were to scatter corresponding gravitons in M theory in 11 dimensions. Right? So scattering amplitudes of clumps of D0 branes should be equal to scattering amplitudes of M theory. And this is from the original BFSS conjecture. Okay, so I'll also say that I didn't write explicitly the polarization data of these gravitons, but that will be stored in the fermionic data of BFSS. Okay, so just for just to be a bit clearer, so I'll define x plus and x minus as x0 plus or minus x10, and then p plus and p minus are similarly defined. So the light-like compactification of this 11-dimensional space here is just x minus has a, well, has a radius of r. And the idea is that we want to, if we have some process going on in 11-dimensional space and this, there's some state evolving with some p plus, where p plus has to be quantized in terms of n over r. We want to keep n over r fixed and then take r to infinity to recover all of 11-dimensional space. So the idea is we keep n over r fixed, and then we take r to infinity, and that has the effect of also sending n to infinity. So that's why
here you consider this light cone quantization and the discrete light cone quantization. Like I mean,
yes.
the usual people, this light cone quantization is that this x plus is like a time and so on. And then also people like I think Susskind proposed this discrete light cone quantization. So you are talking about that discrete.
Yeah, but the idea is that we also want to take n to infinity, and then we want to recover non-discrete. So we're interested in non-discrete, but in this sort of way I've described things here, I've sort of started with discrete, but then taking the limit where you get infinite volume, and then it becomes non-discrete again.
BFSS model can be obtained in this procedure, like a discrete light cone and so on. Yeah. And take the double scaling limit and so on. Or,
yeah.
Okay.
Yeah. Okay. Cool. So, okay, so the large boost is actually doing something kind of interesting for us in the 10D theory, right? So this is dual to a 10-dimensional theory. And if you have a graviton with n units of momentum in 11 dimensions, that's a bound state of ND0 branes in 10 dimensions. And then because of the heavy boosting, the rest mass in 10 dimensions is really big. So, okay, if you take a particle and you boost it in some direction, the momenta in the transverse dimensions will stay the same, but the momentum in the direction you're boosting on will get really, really big. But if that dimension you're boosting in is invisible in the dual, lower dimensional theory, it just looks like you now have particles with much bigger rest masses than their transverse momenta. And that's the non-relativistic limit. So if you have P transverse divided by rest mass is much less than 1, that's non-relativistic. So the D0 branes in BFSS are non-relativistic. Okay, so here's a little bit of a picture which should kind of explain the duality. So here we have 11-dimensional space on the left and 10-dimensional space on the right. So these two black sheets are being identified because x minus is the same as x minus plus 2 pi r. So these two black sheets are the periodic condition of spacetime. And then this blue sheet that's sort of at a right angle to these two black sheets, that's the Cauchy surface, which is evolving forwards in time. Then we have two gravitons. I've drawn them in pink and purple, and they have momenta vectors with these solid arrows, and they also have they'll have some component of momenta in this x minus direction. And this component of momentum, which is actually P plus, needs to be quantized. So in this graviton, it's N1 over R. For this graviton, it's N2 over R. And likewise, they have some transverse distance between them, between the two. Now, if we go over to the D0 brane picture, the transverse distance will stay the same. And each graviton will be a clump of D0 branes with some transverse momenta. And here, N1 and N2 correspond to the P plus. So the holographic dimension is X minus. That's what's not seen by lower dimensional theory. But the holographic dimension is represented in the D0 brane world as just the number of D0 branes. So that's like the variable that's like giving the holographic dimension. Okay, great. So I don't want to go into too much detail about what exactly the BFSS Hamiltonian is, but just so you see it with your own eyes, here are the quantum variables of BFSS. They are matrices. So here xi, where I goes from 1 to 9, are the spatial dimensions of the 10-dimensional spacetime. So here xi are self-adjoint matrices are equal to xia. So these are all just numbers. And here are the generators of un. Okay, I should have changed that, sorry. Here I wrote TA are the generators of sun. I should have just written un. And then likewise, we have these matrix of fermions. So here alpha is a spinor index going from 1 to 16. Here I have a matrix of fermions. And then states in BFSS are functions of these variables. So here's the BFSS Hamiltonian. Yeah, so here we just have the usual kinetic term. Here we have this sort of bosonic potential, and then we have the fermionic term. So this BFSS Hamiltonian is the only Hamiltonian you can write down with the right symmetries. That's how actually you would get it. So it has this UN gauge symmetry, basically, which means that under UN rotations, states don't change. So the D0 branes are like bosons. And it has 16 supersymmetries, which it would have to have. And right, the states, right, okay, so here's just the statement that we have a UN gauge symmetry. So this is what generates a UN gauge transformation on the state, and that should annihilate the state. So the bosonic potential, okay, there should be a little squared right here. Sorry, should be a squared here. The bosonic potential for this Hamiltonian is just trace of sum of these commutators squared. And classically, this can only be at a minimum of 0 when all of these matrices commute for all I and j. And in such a case, all the matrices are simultaneously diagonalizable. So classically, the bosonic variables x can only be at a minimum of the potential when they all commute. And in such a case, the eigenvalues of these matrices correspond to the positions of the n different D0 branes. Now, in this case, the off-diagonal terms in the Hamiltonian, if the eigenvalues are far away from each other, so the D0 branes are kind of far away, then each off-diagonal term is a superharmonic oscillator. And the frequency of this superharmonic oscillator scales linearly with distance of the two D0 branes you're thinking of. So in actuality, this superharmonic oscillator, the occupation numbers thereof correspond to the occupation number of strings stretched between these two D0 branes. So you can think of the eigenvalues of the matrix corresponding to the positions of these D0 branes, and then you excite the off-diagonal terms, and then those you can add strings between them. And that will induce a linear potential between. So this could be considered an emergent theory of spacetime if you wish, in the sense that you have this matrix where there's not really a clear distinction between what's a spacetime coordinate and what's like describing strings, but then in a certain basis, you can see the emergence of the positions of these objects. Okay, so what makes the clumps of D0 branes attract each other? Let's talk about that. So the attraction of far separated clumps comes from strings being in ground states with some associated ground state energy, which depends on the relative distance and velocity of the clumps. Okay, so what does that mean? Okay, maybe I shouldn't say the string in the ground state. Maybe I should say the number of strings in the ground state, or the degree of freedom corresponding to the occupation number, just like how many strings there are. So think about just quantum mechanically particle in a box with some walls, and imagine adiabatically changing the size of the box. So if the particle starts in its ground state and you slowly change the size of the box, the particle will still be in the ground state of the new ground state of the new box. So likewise, there'll be some associated ground state energy for this superstring stretched between these two D0 branes. And as the D0 branes maybe like slowly pass each other, that harmonic oscillator will also have some ground state energy, which is changing slowly. And that ground state energy, if you solve for it, actually corresponds to the effective potential that the two gravitons have with each other. So you could also have more complicated processes where say the D0 brane bound states kind of hit each other and exchange D0 branes and scatter off. That's a more complicated sort of process. Yeah, just simply, here's like the simple intuitive thing. Think about adiabatic box like that. Okay, and this was just something sort of interesting that the Galilean symmetry algebra is actually a subgroup of the Poincare algebra. Not a contraction, I'm just saying a subgroup. So yeah, I mean, I don't really want to you shouldn't look at this too hard. I'm just sort of writing out specifically, but the Galilei symmetry of the lower dimensional theory is just sort of contained in the higher dimensional theory in a very specific embedding, where the Hamiltonian is P plus and the mass is P minus. And there are these boost operators, which are basically boosts minus rotations in a certain direction. Okay, just thought I would mention that. Okay, so now I'm about to talk about the paper. Does anyone have any questions so far? Ooh. Okay, good. So the basic idea is as follows. So the first question we want to ask is, what does a soft graviton mean in BFSS? So in M theory, we can have, say, some particles scatter and there's some S matrix. And then in the BFSS model, we instead of clumps of D0 branes would scatter. So instead of so let's just say we're talking about graviton scattering. Some gravitons with some finite energy, they have some 11-dimensional vector k mu. Then it will become the momentum in the transverse directions and the number of D0 branes. And then in terms of matrices, that will look like one set of block diagonal matrix turns to another one. But now if we insert a soft graviton in the scattering process here, yeah?
I have a question. So when you say transition, what do you mean by this transition in the Planck matrix? So is it
Sorry,
kind
transition?
of yeah, you mentioned that this from the point of the BFSS model, it's kind of a transition, or so what does it mean in the matrix model? Is it you have to calculate the so given you have a given block matrix
Yeah, so you have so you have some state corresponding to some widely separated D0 branes with their center of mass, degree of freedom in like a plane wave or Gaussian wave packet, and then you evolve them forward in time with the BFSS Hamiltonian, and then it'll evolve into some other state. And you correspond that transition element. Okay, good. Then if you insert a soft graviton into this process, that corresponds to one block, which is much smaller than the rest of the blocks. So a soft graviton is a much smaller energy and therefore a much smaller n than the other ones. So it's just an extra little clump coming off. So soft graviton equals D0 brane clump with very few number of D0 branes. And when that ratio of, let's say, these ends to this n is very large, that's the soft limit. So just as a basic graph of what the duality says, in M theory, the soft limit is when the energy of the soft graviton divided by the energy of any of the hard gravitons. And by hard, I mean finite energy. So J is, let's just say J labels the hard gravitons. That limit goes to 0, that's a soft limit. BFSS, it's when the number of soft gravitons, the number of D0 branes in the clump divided by the number in the other clumps goes to 0. So the leading soft term, if you just rewrite this in terms of the BFSS variables, okay, so we start here, J is a sum over all of the hard particles in the scattering amplitude. This is the polarization tensor of the soft D0 brane. Okay. Now it will become a certain, also this EIJ will contain the polarization data of the clump, and this is the inversion tensor from conformal field theory. Okay, so an expansion in omega over S will now become an expansion 1 over n, right? Because as n grows, so let's say nj will scale with n, but ns won't. So the soft expansion is a 1 over n expansion. And the asymptotic symmetries, supertranslations in M theory, will become large gauge transformations of the RR1 form field in the BFSS matrix model. So I'll get to that very shortly. So one thing that this wasn't really a big part of the paper, but this is something I think is very interesting, and I wanted to just talk about this for a moment. In the BFSS matrix model, the bosonic potential has a lot of flat directions corresponding to saying you have a clump and then you break up the clump into 2 clumps and bring them far away. And these are flat directions with an infinite volume of like moduli space. And this infinite volume vacua, instead of vacua, classical vacua, correspond to certain infrared divergences that sometimes come up in BFSS. Now, this infrared divergence in BFSS corresponds exactly to an infrared divergence that comes from the soft graviton theorem. So in the soft graviton theorem, if you have a very low energy graviton, there's an infinitely high probability density. You have to be careful. I can't just say probability, but that it's emitted. And thus, in the context of BFSS, if you were to have some scattering process, the wave function governing the scattering process is always going to leak along these flat directions and is always going to correspond to, say, little D0 brane clumps sort of coming off the big clump. So this is the exact type of infrared divergence that arises from the soft graviton theorem. So it seems very likely that the soft graviton theorem could give us some new information in BFSS that could maybe help us revisit it, right? Because BFSS is a really complicated theory, and people were not really able to make too much progress in it back in the day. But maybe now we've thought about it in the intervening 20 years, maybe we have some new ideas. This could be one such idea. So there's a linking of infrared divergences. Not totally sure what it means, but I think it's very likely to have a lot of content to it. Okay, so just wanted to say that. Now, what is the soft graviton theorem? Okay, so here, I actually don't think I actually wrote down the soft graviton theorem in this talk yet. So here's what the soft graviton theorem is. Just here I wrote in terms of M theory, it could be any theory of gravity in a certain high enough number of dimensions. So here we have a scattering amplitude where we insert a soft graviton with a momentum Q sub S, where S stands for soft, and some polarization data for the soft graviton. So it's just equal to the amplitude without the soft graviton times this factor. Now this factor is a sum over the hard particles, where here eta j is 1 for outgoing particles and -1 for ingoing particles. So it's just whether the particles outgoing and ingoing, and then this factor here. So we can think of this factor multiplying the amplitude as a phase shift. So in a scattering amplitude, your particles are always in momentum eigenstates. Not always, okay. Oftentimes your particles are in momentum eigenstates. And if you do a super translation, think about a plane wave hitting null infinity. If you do a super translation on such a plane wave, it will just translate that plane wave by a phase shift, right? Because it's in a momentum eigenstate. And the sum of all these factors here can be thought of all the infinitesimal phase shifts from doing a super translation on all the hard particles. So you can, if you like to think about this as a conservation law, which it is, you think about this as like the soft part of the soft charge. You call this like the hard part of the soft charge. I won't go too into that, but in any case, this slide isn't too important. But if you rewrite the, I'm sort of defining variables here. So the momenta of the soft graviton in 11 dimensions, you can parameterize it in a certain way with this vector vi. So this is a, let's see, if this is an 11-dimensional vector, then vi is a 9-dimensional vector. And that corresponds actually to the velocity of the clump that in the 10-dimensional Galilean physics. So this is a very convenient parameterization that actually appears a lot in celestial holography. Although I don't think anyone has ever noted that this corresponds to a Galilean parameterization, but whatever. And then we can parameterize the polarization data in a similar way. This is just a very particular nice choice of polarization vector. And if we can rewrite the soft graviton polarization tensor as some sorry, it's late. What do you call it? As some components Eij times this basis that I've defined here. Okay, so Eij is just labeling the polarization data of the soft graviton or the soft clump. And then if you just simply rewrite the factor in terms of these variables, you get the following thing in terms of BFSS. So here I've used the BFSS conjecture that we can just replace the amplitudes in BFSS. Sorry, we replace the amplitudes in M theory with the amplitudes in BFSS. So here we have the number of D0 branes in the clump Nj divided by the number in the soft clump, little ns. Here we have the polarization data. Here we have the velocity of the soft clump. Here you have the velocity of the hard clumps in this very particular combination. Here we have kappa, which is the gravitational constant, basically. And then here you have the BFSS amplitude. Okay, so that was a lot. Okay, but
so can you already explain more about this BFSS amplitude?
Yeah, explain more about it.
Of course, we know what amplitude is, but some more detail about how you define this BFS. Like this is in a sense, this is just one quantum mechanics of the matrix.
Mhm.
So there, how you is it just usual definition of this amplitude in this quantum mechanics, or like in quantum mechanics, I don't know how to define this amplitude.
Yeah, actually, could I come back to that in like 2 slides?
Yeah,
and
yeah,
maybe
sure.
I'll
No
say
problem.
something.
Yeah.
Okay,
Yeah.
I think I might have a picture in a few slides that might. Okay. Okay, yeah, actually, I think the next slide, or no, okay, yeah. Actually, I'll just skip to that picture now. So ignore this thing I've written here. But here we have some wave packets of D0 branes, and they're in their wave packets are sharply peaked in momentum space. So even though the position uncertainty grows with time, the angular width is very small. So you can think of some wave packets which come in from the past, and then they go in. This is in the scattering region where they basically travel on their own, and then they enter some sort of interacting region, and they scatter out into all different clumps. So that's kind of, does that answer, was that your question, or I don't know. So in terms of actually computing such a thing in BFSS, it's actually extremely difficult, and there's.
Oh, I see. So I'm asking practically how.
Okay. Sorry. Okay, yeah, I'm sorry. So practically, this is very tricky. So one of the most popular sort of checks that was done and there weren't that many checks done of BFSS. There were a few, and one of them was basically where you sort of did this background field formalism with the center of mass of the clumps. So this is described in Becker Schwartz's book, and a really good review, by the way, for learning what BFSS is the review by Washington Taylor. It's like about, I think, 50 pages or something. I recommend that. So basically, you take the diagonal terms, you make them classical variables, and you just sort of take them to just be two, let's say, D0 branes, which are going on straight paths and have some impact parameter. Then you integrate out all of the off-diagonal terms corresponding to the strings, and you compute the effective potential of these two clumps traveling like this. And then once you have the effective potential, you can link it with an amplitude from Born's, the Born expansion, where you just, the amplitude is the Fourier transform of the effective potential. And that's like one scenario where you can compare these two things in the same. Now you'd also, that's a very specific scenario. More generally, you'd like to have them exchange D0 branes and smash head on. That's the thing about BFSS, is that it was really complicated, and it was difficult to make progress in it because the theory is so complicated.
So here in the chat, there is a question. Is there an analytic form of the BFSS amplitude? Probably no. Or
no. Yeah. I mean, really, not much. Not like a super. Not. So here's the thing, right? BFSS was never able to give physicists anything new that they couldn't compute before, to my knowledge. I'm not the biggest expert in the world, actually, on like the state. There were many papers written in 1998 or so about this topic, but it wasn't really useful in the sense that ADS-CFT is useful for doing unique stuff on both sides of the duality, and then getting interesting stuff on the other sides. It kind of only ever went one way, where you tried to check things about, let's say, supergravity amplitudes, and check it to like in some limit or some order or some specific scenario, and it worked. And it was devilishly hard to even do that. So yeah, so BFSS is a topic where a lot isn't known. So yeah, so the point of this paper was really to like revisit this old duality and just ask some 0th order questions about how asymptotic symmetries are embedded in the matrix model, right? Because this is a flat space duality, and in flat space we have asymptotic symmetries. So we're just asking 0th order. This is a 0th order adventure in BFSS. That's sort of maybe the context of this paper. Yeah. Cool.
So
So-
what is the VS in BFSS?
What is, sorry?
VS, VJ, I mean the V.
Can you say that again? Sorry.
What is the how VJs are defined?
Oh,
in
VG, sorry, yeah.
Yeah.
So yeah, so this is just a parameter. This is a 9-dimensional vector, which just parameterizes a null vector for the momenta of the soft graviton. So here we have the momentum of the soft graviton in 11 dimensions. This is an 11-dimensional vector. And then VS is a 9-dimensional vector. And in this particular combination, you can compute Q squared equals 0. Omega S is a scale.
So this is basically momentum.
Yeah, it's basic. Yeah, exactly. It's basically just momentum in it's velocity. It's the velocity of the D0 branes.
I mean no, I mean in BFSS. So
Yeah.
it cannot be represented as something of a matrix or. Okay.
So yeah, so I guess it didn't really. So classically, if you think about the matrix with some entries, then the diagonal entries will grow as like V times time in the asymptotic region. So that the eigenvalues themselves are growing with time in the asymptotic region as V, the velocity times time. So it's parameterizing the eigenvalues of the matrix.
Okay.
Let me take a step back though to this expression I had here. So just rewriting the soft graviton theorem in terms of BFSS variables, we find this proportionality with n sub j, the D0 brane charge. And that makes this expression look a lot more like the soft photon theorem, because in the soft photon theorem, we have charges, the charge of particles out front here. So that makes us, want to ask the question, is the asymptotic symmetry group, what's the asymptotic symmetry group of non-relativistic gauge transformations? So C mu goes to C mu plus partial mu of theta, because now we have this very seductive, connection, like, oh wait, our super translations actually gauge symmetries of the one form field, right? Because the D0 branes are charged under the one form field. But we have to remember the BFSS world is non-relativistic. So what's the asymptotic symmetry group for a non-relativistic theory? And I have not seen in the literature anyone really ask this question. So we're sort of on our own, and we have to say, well, how do we define such a thing? But if we remember from the beginning of the talk, I discussed how gauge transformations asymptote to functions just of x over t, the spatial x over t. And so that should be preserved in the non-relativistic limit. So you can even think of, let's just say that condition will be preserved in the non-relativistic limit. So we will define the asymptotic symmetry group of non-relativistic gauge transformations to be all the gauge transformations which, as t, and how we're talking about t in the non-relativistic world, goes to plus or minus infinity, it will only become a function of x over t. So here is the picture again. We have these BFSS clumps scattering, and then they go in the scattering zone, and then different clumps leave. And on these lines passing through the origin, any function that's a function of x over t and is a constant passing through the origin will take on a well-defined value at each particular clump, because the clumps have a small angular width. And because they have a small angular width, this function will have a well-defined value on the whole clump. So now we can couple the matrix model to a background one-form gauge field with the following coupling. Now, this coupling was found by Washington Taylor and Mark von Ramesdonck many years ago. So they actually had a paper where they wrote all the couplings to external fields. So briefly, let me just say, okay, what I've written here. This is a term in the action which should be added to the BFSS action, where here C mu is a background gauge field. Here we're summing over an integer, and we're summing over all of the derivatives, the spatial derivatives of C mu at the spatial origin times the sort of moment, this multipole moment term for the matrix. So writing it out here, it's a trace over the symmetrized average of these matrices here. So I just mean it's an average over all of the orderings of all of these, n+1 different matrices. So you just order them in all the directions, take the average. That's what that is. There's also a fermionic term, but that doesn't matter for reasons we discussed in the paper. Maybe I don't want to get into that now. There's a fermionic term. And this thing I mu here is just the four momentum of the B0 brane in the non-relativistic world. So the zeroth component is proportional to identity, and this is proportional to the velocity. Okay, so once again, this is the four momentum. We plug it into this symmetrized average over trace thing. You plug that over here, and this is how you couple the matrix model to a background gauge field. This is a very specific form of a coupling because this has to be UN gauge invariant, which is very basically enforced by just having a trace here. And it's also supersymmetric if you are at the fermionic term. And okay, so this is sort of like a generalization of just the standard coupling of a field to a point particle, right? Where you just have the integral over C mu and then times the velocity. But because the matrix model has matrices and not just velocities, and you have to, you can't just like write the velocity of the zero brane. It has to be a matrix in terms of matrix variables. And that's how you accomplish that here. Now, quantum states, quantum wave functions are just functions of classical variables. And the classical matrices, so in this case, the wave functions are functions of matrices. And if you ask, okay, for asymptotic states, which are very sharply peaked wave packets, right, in momentum space, as the wave packet gets sharper and sharper peaked, there will only be certain classical configurations that the wave function will take a non-trivial value on. So as it gets sharper and sharper peaked, there's only sort of localizes on certain classical configurations. And what are those classical configurations? And how do those variables scale with t, right? Because t is getting very large in the asymptotic region. Well, in dark gray, the diagonal elements, those will be the velocities of the particles, and those grow with time. So these are the classical variables that are growing with time that correspond to the center of mass motion of the clumps. Then in the middle gray, these are the degrees of freedom of the clumps that don't correspond to the center of mass motions, everything else about the clump, which should actually be in its ground state. So because that is just sort of staying the same, that the size of the clump isn't changing with time, is let's say the radius, those will be constant as time gets bigger and bigger. Then all the stuff that's off diagonal, that's not in the blocks, well, those are described by superharmonic oscillators. And remember I said that the frequency of these superharmonic oscillators scales with the distance between the clumps. And the distance between the clumps is growing linearly with time. And if you have a superharmonic oscillator in its ground state and the frequency is growing linearly with time, then the width of the Gaussian will be shrinking as 1 over the square root of t. So these are going to 0, all this stuff. This is just to say, remember, these are the classical matrices that the asymptotic states take non-trivial values on. And remember that when you do a path integral, you're always convolving the boundary condition of the path integral with your initial and final wave function. And so if your initial and final wave function is only non-zero on these kinds of states, and here we have this term we've added to the action that we want to say convolve the boundary conditions with, then it turns out that, if you plug in C mu is a total derivative. So you plug in C mu equals partial mu of theta. This becomes a total derivative with respect to time. And if you plug in the exact form of the matrix I've written here into these matrices here, this just becomes once again, a total derivative term that localizes on each clump, because the gauge parameter theta, which will be included in this because C mu will be the derivative of theta, that will localize on each clump. And thus we'll be able to write the following expression. So if we have a BFSS amplitude with some out and in state, and we put it in a background pure gauge field, then this can be related to the gauge field, the amplitude without any gauge field with this factor here. So here we have theta of, and then x over t just becomes the velocity. And then here we're summing over nj over r. So, okay, I know that was a bit of a mouthful, but this is how you couple a pure gauge background field, and only a pure gauge field where the gauge parameter satisfies the asymptotic condition. I said that it's only a function of x over t, and then x over t becomes the velocity of different fields, okay? This is how coupling it to such a background field affects the amplitude. Okay, if you define a particular gauge function that depends on the polarization data E and the velocity of the soft graviton with this very particular function, then you can get, I guess what I would say is the main result of this talk, which is that if you insert a clump, a soft D0 brane clump into the amplitude, and this is evaluated, with no background gauge field, this actually generates this background gauge field on the amplitude otherwise. So this has the exact form that actually not only the soft theorems have, but just the general conservation laws from gauge theory have. They always have a hard part where you insert, they have a soft part where you insert the soft clump, and they have another part where you sort of implement the gauge transformation on all of the hard particles. So in other words, through this duality, we have equated two asymptotic symmetries in two different theories. We have shown, this is a result, that supertranslations in M theory correspond to gauge symmetries of the one form field in the matrix model in type 2A string theory. Now you might wonder, okay, well, Noah, you coupled this to a background gauge field. Isn't that sort of strange? I would say, yes, that is actually strange. But notice here, this is an equation. On the left-hand side of this equation, the background gauge field is turned off. And on the right-hand side of the equation, the background gauge field is turned on. So inserting the clump has the effect of turning on this background gauge field. In another sense, it's kind of taking you to a different vacuum of the theory. So in QED, in quantum electrodynamics in 4 dimensions, in a textbook, we usually mode expand the gauge field around 0. We write a mu in terms of Fourier modes around 0. But you can also expand around different classical backgrounds. And those other classical backgrounds are still in the theory as coherent states. You can access those other backgrounds by just making a coherent state that would then get you to these other backgrounds. So just because you're expanding around a background doesn't mean it's not in the theory. In particular, in the case of large gauge symmetries, we can if we mode expand a photon, we can also not mode expand it around 0. We can mode expand it around a pure gauge background. So maybe mode expand around partial mu of theta for some theta. And those other backgrounds are actually, they were still in the original theory. And you can get to them by inserting an infinite number of soft photons. So inserting an infinite number of soft photons takes you from one pure gauge background to another. And thus, that's the same thing we have found in the BFSS matrix model. Inserting these clumps gets you a new background. And what would be really interesting is to think, is there actually some way that these variables of this other background in the BFSS matrix model can actually be written in terms of matrix variables? So I sort of suspect there might be, okay, let me give you an idea that I think there might be some to this idea. This is just like kind of speculation. So oftentimes when we do BFSS calculations, you think about having a large matrix, then in the end, we take the size of that matrix to infinity. But infinite dimensional matrices are actually not, they're not really finite dimensional matrices that are made big, because there can be special stuff about them. For instance, infinite dimensional matrices sometimes aren't diagonalizable, and they sometimes have interesting properties about them. So it would be very interesting if maybe these other backgrounds were in some degree of freedom of BFSS, that were maybe some non-diagonalizable degree of freedom in the matrices or something like that. It's something like that's possible, but I'm not totally sure how to flesh that out. But yeah, I would say that this has been, I'd say, the main result of the talk. I'll end with one final strange thought, just while I'm sort of opining. Supertranslations in 11 dimensions are completely captured by non-relativistic gauge transformation in 10 dimensions. Oh, sorry. Oh, I didn't. Okay, sorry. And it's weird. Okay, so this is an example of two asymptotic symmetries being related to each other, which I've already said. But one thing that I think is weird is that the dilaton and the graviton in 10 dimensions don't play any part here, right? Because when I talked about Kaluza-Klein theory in the beginning, I talked about how the graviton in higher dimensions becomes graviton plus photon plus dilaton in lower dimensions. But the graviton and dilaton in lower dimensions have no part to play here. I'm not quite sure why that is. That's honestly kind of strange to me. I guess it has something to do with.
Can I ask you a question?
Yeah, totally.
So,
oh, but actually, why don't I just end my talk? And then I'll just say, okay, that's the end of my talk. And thank you very much for listening.
Thank you very much for the very clear and the nice talk. Yeah, then please ask question. Maybe Akil.
Hi.
Sure.
Like it was a very nice talk. Like it was like everything was very clear. So like I want to ask this. Like so from a Kaluza-Klein point of view, isn't it natural that like you would the super translations in the M theory would become the soft photon theorem and the something like a U1 gauge coupling to the BFSS, and the super rotations should be something like a graviton and so on. Like,
can you ask that again? Sorry. So isn't it clear that
if you want the gravitons in the lower dimensional theory, shouldn't you really consider super rotations or something in the 11 dimensional theory? From the Kaluza-Klein point of view, right? Because there's a one parameter in the super translation and on the spatial circle, and super rotations would be like a more analogous to a tensor in the something. I was wondering like if that made sense.
Yeah,
I mean, of course, super rotations in the M theory also should have an analog in this way of looking at it.
Yeah. So actually, my two collaborators, Tianli and Adam, are now actually thinking about this exact question. That's still, I think they're still in the preliminary stage of thought. Although I think there's actually, right. So that's I think that's sort of what they think. I think another possibility is that it could actually be like the two-form field. Maybe I won't say too much. Yeah, there are different options for how super rotations should be.
Oh, because you're saying rotations are antisymmetric or something. Is that why it's a two-form
Yeah,
field?
there's other. Yeah, I think I can't comment too much on this, but something like that I think is going on.
Okay.
I should also say that like the story, just for full disclosure, like the story is said in the beginning of like large gauge transformations are, you know, things that satisfy the fall-offs divided by trivial things. Yeah, there hasn't really been like a detailed study of like fall-offs in a like 11-dimensional gravity. Like odd dimensional stuff already is very confusing to begin with, but usually, so in 4 dimensions, the story works like very clearly. Then in higher dimensions, usually like the asymptotic symmetry group is like not as well studied, and oftentimes people sort of define it to include supertranslations, which is fair because the conservation law from supertranslations always is the soft graviton theorem. So you can always allow it. But yeah, stuff works kind of differently in 11 dimensions. So actually, I'm not actually, so yeah. So supertranslations in 11 dimensions, and actually more specifically just fall-offs of different things, are not very well studied. And super rotations are always more complicated than super translations. So I actually wonder if there are a lot of subtleties there too.
Hi. So I want to ask, I have 2 more questions, like if it's not troubling, like,
Sure,
so
yeah.
one question is like, in spite of having, like, if I had a large and matrix theory, like in spite of whether whether it really came from something string theory or something like how BFSS was derived, could I still be like coupling it to a gauge field and trying to write down the soft theorem you wrote down? Like, would it make sense? Like, as like, or
Just
would
any
there be
matrix model?
just any matrix model, if I like couple to a gauge field, and would there be an analogous relation? Like, I'm just wondering, like,
Yeah.
just from completely a matrix model point of view, what would be the analog of this soft theorem relation you had?
That's a good question.
Whether
Well,
I should be expecting something like this, like where
I don't
where the
think-
matrix still fractionalizes like into smaller sub blocks and so on, but I could write this.
Yeah. So I think maybe, so I would expect that if this story has lessons to be learned in other matrix models, this sort of picture here is probably the one with the best chance of being applicable to other matrix models. You have matrices which can have subblocks and have eigenvalues with some emergent notion of some variables, and any sort of sense in which you have, like, let's say a small block, or you have leaking in some flat direction to separate some blocks or something like that. I think the sense in which that would correspond to like an infrared, thing, I think that has a high chance. Now, I think coupling it to, I feel like the background gauge field is sort of a peculiarity of this particular setup we have here. And I feel like would not really generalize in other contexts, but maybe it would. Yeah, I don't know. Just answer your question.
Okay, thanks.
But I think there could very well be like senses in which this does have lessons.
So can you do this kind of picture in the new? Do you think it's possible to confirm numerically this you know, this BFSS model is very, very difficult to analyze because it's
no, I don't think so.
model.
No,
So
no, I don't think so. So there is numerical work done.
yeah, like a Monte Carlo or
Yeah.
this simulation, but this check this soft theorem in the Monte Carlo, it maybe it's difficult.
No, I don't think so. So yeah, so that stuff is usually about computing like partition functions. And already actually they have to deal with infrared divergences coming from the infinite volume of these flat directions, usually with some sort of IR regulator or putting in a box or something, which is kind of unfortunate because that's the exact thing you'd want to study. But in any case, the reason that this wouldn't really work for Monte Carlo is that the number of variables scales very, very violently with n. So you have n squared variables, and then functions of n squared variables are really, like, that scales even worse. And I think most of those things usually go to n equals like 10 or 16 or something like that. And the whole regime where this works is for n equals infinity, for the soft graviton theorem, because you need you need n getting big to get these little blocks like this. Now, I think if you could do stuff with Monte Carlo, what the real thing to do would actually just be to check the original conjecture. I mean, there are people who don't think the original conjecture was right, for different reasons. There's not like, there were some like very, you know, not highly non-trivial like checks of it, but not as many checks as one would like. So maybe the conjecture's not right, or maybe it's not exactly right. I mean, I think most people think it's right as far as I know, but you know, whatever. Anyway, I mean, there's also non-trivial reasons to think it's right. But if you could do Monte Carlo stuff with it, nobody's doing simulations to compute amplitudes of BFSS. That's like really out of the question. Because like the form, nobody even knows the functions. It's like the general form of the functions for these like ground states. They know that they exist. They don't know what the form of the function is. So yeah, that's really out of reach. So everything in BFSS is either really simple or really complicated, like anything you're going to do with it. So this paper sort of tried to stick to the simpler stuff, and thankfully everything we did worked out in like a very clear way without having to do any like getting really nitty gritty with BFSS, which usually ends up being inconclusive anyway. So we wanted to say things which we knew were true, yeah, which we knew, you know, were true and non-trivial. So that's what we tried to do.
Okay, thank you. Is there any other question? If not, let's thank speaker again. Yeah, thank you very much.